Hi everybody, this is just going to be a review for amino acids, and I hope it can be at least a little bit helpful to you. If you have any ideas for any other reviews that you'd like to be made for this class, any other issues that you're having trouble with, just let us know and we can make those too. So we're here to help, pretty much. Anyway, I'm going to start off by drawing the main structure for amino acids, and it starts with a alpha carbon in the middle attached to the alpha hydrogen on the right side, a carboxylic acid, which is a carbon double bonded to an oxygen, and then another oxygen, which is either O- or OH. And then there's also the amine group on the left side, NH3+ or NH2. And as you can see, I've made this fully protonated just for simplicity, but in physiological pH, this would be NH3+, but this would be O-. But just keep that in mind, that this isn't physiological pH, this is just how I've drawn it. And then the carbon is also bonded to the R group. And so as you see, I've drawn the NH3 on the left side and the H on the right side. And what that means is just that this is an L amino acid. In your body, all you have is L amino acids. So that's all you have to worry about in biochemistry. You don't have to worry about the D amino acid, which is just when the NH3 group is on the other side. So don't need to worry about the D. Just the L. But that's not to say that this isn't a chiral carbon. As you remember from organic chemistry, any carbon that's attached to 4 different groups is going to be chiral. And so this carbon is attached to a hydrogen, a carboxylic acid, an amine group, and then the R group. And those are going to be 4 different groups, which makes it chiral. It's not related to R and S stereochemistry. L and D is not related to R and S stereochemistry. L and D is just nomenclature. R and S is also nomenclature, but L and D has nothing to do with which direction it rotates the plane of polarized light either. It's just nomenclature, that's it. So the only molecule, the only amino acid that's not going to be chiral is glycine, and that's because this R group is also going to be a hydrogen. So there's not going to be 4 different groups attached, just 3, the hydrogens, carboxylic acid, and amino groups, the amine group. And so that's just 3. So glycine is the only one that's not optically active. It's the only one that is not chiral, glycine, because the R group is an H. Okay. Moving on. So this R group is going to be different for all 20 amino acids you have in your body. And I have a chart here that I think is pretty handy. This is from Leah Forsai. She has a whole bunch of YouTube videos if you want to look her up, and she also has a whole bunch of fun, interesting figures if you need help. I think this one's pretty handy. So what you need to know for this class is the different groups that amino acids can fall into. They could be nonpolar, polar, acidic, and basic, which are also called charged. And then Dr. Vugmeister also wants you to know if they're aromatic or not. And so if you remember from organic chemistry, an aromatic group or an aromatic ring can be a benzene ring. So in organic chemistry, you can have more than just benzene rings be aromatic, but for amino acids, just worry about benzene rings as being aromatic. And so the amino acids that have these rings are phenylalanine, tyrosine, and tryptophan. So these are aromatic. And as you can see, phenylalanine also shows up here, tryptophan is here, and tyrosine is here. So it would be under both groups. Phenylalanine would be both aromatic and nonpolar. They don't contradict each other. They're just 2 different groups that they can both fall under. Okay, so here you can see pKa is a big deal. So what makes amino acids pretty special is that they can act as either a base or an acid. Just a review. In organic chemistry, you had to know two different versions of acid and base, 2 different descriptions. There was Bronsted-Lowry, and there was also Lewis acid and base. But in this class, or for now, all you need to know about is Bronsted-Lowry, and that has to do with whether or not it donates or accepts hydrogens or protons. And I don't know how to spell. So acids are proton or hydrogen donors, and bases are hydrogen acceptors. So you can see up here that every amino acid has at least 2 hydrogens that it can either donate, or it can either accept 2 hydrogens or donate 2 hydrogens. And so these hydrogens right here, the alpha hydrogen stays put, but the one on the carboxylic acid and then the one on the amine group are the ones that it can either donate or it can take up. Those 2 right there. I'm going to circle those in red. And then on certain amino acids, there's also hydrogens on the side chain that it can either donate or accept, but not on all amino acids. Some of them, it's just these 2, but other amino acids, there's also side chain hydrogens. So just an example, I'm going to draw lysine here. So that's carbon. Sometimes it's not drawn split up like this. Sometimes it's just drawn as COOH, and that's also acceptable. There's also NH3 plus hydrogen, and then lysine has CH2, 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 and NH3 plus. This is the R group. Let me circle the R group. This is the amine group. This is the carboxylic acid group. And this is the alpha hydrogen. But you don't need to worry about the alpha hydrogen. That one doesn't really do anything. It just sits there. So what you need to worry about is at which pH are these hydrogens going to pop off, and how do they do that? So let's just say at a pH of 0, that's the environment is going to be really acidic, because you know pH, it goes from 0 to 14. And this is acidic, and this is basic. So at a pH of 0, really acidic, there's going to be a whole lot of protons floating around in the environment already. So the amino acid's not going to need to donate any hydrogens. There's going to be nothing to donate hydrogens to, because there's so many hydrogens in the environment already. So it's going to be fully protonated at 0. And that's from, this is lysine right here on the chart. That's from 0 to 2.18. It's going to be mostly protonated. But then from 2.18 to 8.95, it's going to lose its carboxyl hydrogen. So that's this one right here. So 2.18 to 8.95, this is going to pop, this hydrogen's going to pop off. So I'm going to redraw it without that hydrogen. And now it has a minus charge. Okay, so that's from here to here in this range. And then from 8.95 to 10.79. Oh, I need to stop this and start again. Okay, from 8.95 to 10.7. It's going to lose the alpha amino hydrogen. So that's this one right here is going to come off. So now you're going to have COO minus, that's still a negative, negative charge. There's the hydrogen. This is going to be NH2, CH2, 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 CH2. And NH3 plus. This is the side chain, and so that one is going to pop off from 10.79. This should be 9. 10.79 to 14. And that's the end of the scale on the pH, the end of the pH scale. So that's going to be COO minus. You can see these carbons are keeping their hydrogens. Those aren't going to come off at all. That's pretty stable. And then this is going to be NH2. And that's it. That's it. Those are the only hydrogens that this amino acid is going to lose the whole time. That's the end. So from the pH of 0 to 2.8, it's going to look mostly like this. There's going to be some molecules that have lost their hydrogen, but mostly it's going to be this. As you get closer to 2.8, more are going to lose the hydrogen. That's why it's a curve. It's not just like boxes. It's more of a curve like that. From the pH, when the pH is 2.18 to 8.95, it's going to look mostly like this. When the pH is 8.95 to 10.79, it's going to look mostly like this. And from 10.79 to the end to 14, it's going to look mostly like this. So when you're looking for the isoelectric point, that's when this molecule has no charge. It's neutrally charged. So what's the molecule? This molecule is charged. At the very end, it's charged. And it has a negative charge because this is the only charge on that molecule. There's no positives. So it's going to be -1. This has a negative and a positive. Those add up to 0. This has a negative and 2 positives. So that's positive charge. And then this one has 2 positives and no negatives. So that's +2. So when you're looking for the isoelectric point, you want to look at when the molecule looks most like this one, because that's when it has no charge. So that would be the range, the pH range would be between 8.95 and 10.79. And that's these two. And that is when you can find pI. So this would be pK1, this would be pK2, and then this one would be pK3. And remember, we're just looking at lysine here. You don't have to worry about all the others unless those are involved in your peptide also. But if you want to find the isoelectric point for this amino acid, you're going to take these two numbers. So that's pK2 plus pK3 divided by 2. So pI equals 8.95 plus 10.79 divided by 2. And let me erase some of this because it's really messy. Just erasing my chart. Okay, so I think the PI would be some number after you've calculated this. I'm bad at math, so I'm just going to leave that there. But I have a titration curve for lysine that I got before I started this. So let me just show you how that matches the math I just did, the work we just did. Okay, so they also have lysine drawn out. It's a lot cleaner than mine. So PI, they have here also. They have pK2 plus pK3. That's what we had That's what I had chosen here, pK2 plus pK3. So 9, that's about 9, plus 10.5, it's close enough, divided by 2, so it would be 9.75. That would be pi, and that shows up right here on the graph. That's between pK2 and pK3, so that's when it's going to be negatively, or that's when it's going to have no charge. It's going to be neutrally charged. And that's also called, it's also a Zwitter ion because it has a negative charge and a positive charge, but its net charge is neutral. So this would be really great to work as a base, this molecule right here. Or not as a base, as a buffer. That's pretty much it. I'm not going to go into too much detail about drawing titration curves because Isaac, I think, made a review video about that, but we can do more if you need more help with it. But this is just the basics about amino acids. Yeah, I think that's it.